today we're going to be talking about some of those forces. So what have you guys learned about forces so far? Okay, so forces can be push, or they could be a pull. What else have you learned?
If you push it like this, it don't move.
Okay, so if we have something and I could have a push in two different directions, like say that this is positive and this is negative. And the reason why I'm saying that is when we think of a regular sort of y-x graph, this is going in the positive direction. If I extend it, this would be the negative direction. That I could have it that there could be forces acting on stuff, but we're not moving. Okay? Like if I push on Jack's book here, I can push and push and push and it doesn't make a difference because the table's pushing back up. Okay? If I have these that are the same size, say that this is 5 and this is 5, think about all forces if they're equal to each other, but they're going in opposite directions.
You call them
You may.
a balance?
Yes, these are balanced forces.
You are hacking that.
Woo. Balanced forces. Now, does this up here look like it's balanced forces?
No.
No. Pushing one direction.
It's put, it's,
It has
In
to.
this
They're
case,
both
they're
positive.
both in the positive direction. One's
Yeah.
pushing the box, one's
One.
pulling the box.
but if,
But
They're
they're
not
still
balanced
going the
because they're
same
still
way.
going the same direction. They're just like doubling up. That's
Isn't
like
that a
when
net?
literally you have that friend that's like dragging you down the hall and there's someone behind like pushing. That's not balanced.
Isn't
That's
it a net
doubling
force?
up. That's teaming up.
Isn't that a net force?
Yes. Okay? When we add up all forces, that equals, you get from there a net. Okay, so all the forces in the x direction, if I add them up, here my net force. If we assign these same values, we said that this is a 5 and this one is 5. Here, my net force would be plus 10. Here, my net force, we're going to say that this one was 5 plus 5. So that equals plus 10. Here we had 5 plus negative 5.
Which is it?
So that's 0. Net force is 0. What kind of units do forces have?
They have
SU units are,
SI units?
SI
units are neutron.
Newtons. Okay? So the SI unit is something called a Newton. It's just a capital N. N-E-W-T-O-N, named after Sir Isaac Newton. Okay? So we measure things in newtons. So this could be like plus 10 newtons, 0 newtons. It's looking pretty good. You guys learned a lot yesterday. Okay, let's see. So forces are pushes and pulls. No, it's not where I need to be. There we go. Okay, so we've talked about forces, we've talked about the unit of measurement. I think we covered a whole lot of it. We're not gonna go into the kinetic and potential energy here.
What about the laws of
We will, but we haven't got there yet. Like, you guys just took notes on forces yesterday. I don't wanna talk about Newton's laws yet. Okay? That will happen a little later in the week, but we will talk about it. Because here's what I want you guys to keep in mind. You already know what your test is. Right? What was the very first item on the test?
force.
It was about the forces. I needed to show an object, whether it's an object that is sitting there not moving, or if it is something that is moving, like a rolling ball or a driving car. Okay? You had to show me an object and describe the forces that are on it. Okay? So, give me some examples of things that are pulls. Can you give me an example of something being
A
pulled?
door.
What? When you pull on the taffy and you stretch it in both directions?
Slime.
Slime.
A dead body.
Okay, slime, you can pull with your hands. What if I just literally hold it and I allow it to drop? What force is pulling it this way?
Good, gravity.
Gravity. Okay, so let's start talking about some of those forces. We could have pushes and pulls. What happens, okay, we already talked about gravity that's pushing things down or pulling things down, depending on how you look at it. That's acting from up above. Okay. Now gravity is it's really a force of the acceleration towards the earth. Okay? And gravity, that acceleration is 9.81 meters per second squared. If I want to figure out what force is acting on this, I need to know what is the mass. Okay, I need to know how many kilograms this is, because a Newton is a kilogram times meters per second squared. It's going to be like if this were 10 kilograms, then I know that this would be 10 kilograms times 9.81 meters per second squared. And so that would be 98.1 newtons. So this would be the force acting on a 10 kilogram object. That's the gravity. Now, here's something that you definitely don't know. Do you know what force is pushing up your feet as you're standing on the floor?
No.
Like there has to be, right? If there wasn't a force pushing you up, you would literally fall through the earth.
What?
You would. If there was just gravity acting on you and there was nothing pushing back up, you would just keep going in that direction. Something has to push back. If I don't have that, and I only have that force of gravity, it would just continue forever, ever, ever, ever. Something has to stop you. No, it's not friction, because I don't have friction necessarily just by standing here. Like, there's no friction. But there is a force that acts upwards, okay, perpendicular to the surfaces that meet.
Is it left force?
No, I don't know if they even told you in your textbook. I don't think they cover it quite, yes, no. I don't see it here in the book, but it's an important one that you need to know. This acts on your feet, it acts on the table legs. There's this thing that pushes up, and this is called the normal force. Okay, this is only when it's touching another surface. It's not acting in midair. Okay? I don't have a normal force. If I'm holding the book out like this, like there's not a normal force right now. It's just the forces from my arm and from gravity. Okay? But if I put this book down on the table like that, the reason why it doesn't continue and fall because of gravity is because a normal force pushes back up. We don't fall through the earth because the ground gives us a normal force that pushes us up and just keeps us in place.
Wait, but isn't this a solid? Like, you can't just go through the solid.
But that solid is providing you that force. The that surface provides that force known as the normal force. Whenever we have two surfaces come into contact like that, and we have no motion, that's because we have that normal force. All you need to know is when we have surfaces come into contact, you have something that's pushing up called the normal force. Okay, although any problem that you would be given, you would know exactly how much, what the value is. You appear to have more questions, so you do?
Is it like quicksand? Like, if you step in quicksand, you slip through. Is there no more force acting on it?
There,
Just gravity.
in that case, you would not have, like, in the case of quicksand, if we had something that was a liquid, essentially, you are not going to have normal force. You would have friction, there still would be other forces. We're talking about something in contact with the solid. Like this is, whenever I am against a solid surface. Whereas a quicksand is not considered a solid. All it is like the floor pushes up, your, table legs push against the floor, the surface of the table pushes against the book, against you also have a normal force right now between your bottom and your seat.
Why doesn't it work on, let's say, like liquid or gases? Is there?
Because there is not a solid surface for the two things to push against. Basically we're saying the force down and the force up are meeting to keep it in position because we have solid things. Okay? If I have a liquid or a gas, I'm going to be able to, if I have a solid up here, push things around. Okay? This doesn't allow for motion. I can't push any further because that force is pushing back. So it only works when we talk about a solid, when we're putting something on a solid. If I try to stand on water, the water is not going to have enough force to push back because it's just going to move out of the way. That's why we talk about solid surfaces. Okay, so we talked about different pulls. What are some different pushes?
Pushing open a door?
Pushing open a door.
Putting the brakes on.
pushing the brakes,
Yeah.
applying the brakes. Now, the pushing the brakes actually gives us
Pushing up.
another force too.
Resistance.
Pushing
We
up.
have some sort of resistance that if I have a tire and what I do is I apply the brake, even though I have, say, a velocity that's going this way, okay, I have a force here of our velocity. I will also have a force moving in opposition, going this way. That is our force of our friction where the tire is moving the road. Okay, that car also has gravity acting on it too, the force of gravity. This also has a normal force where the tire meets the road, the ground has to push to make sure that it doesn't continue just due to gravity. So this is important to know that I'm going to have forces that can act, that are pushing or pulling in the x direction, negative x direction. Okay? Positive y, negative y.
Alright, thank you.
Any of those four directions, I can have forces. I could also have forces coming this way. I can. Those you're not going to be dealing with until you get to physics, okay? And they start breaking things up into, hey, well, what's the x portion and what's the y portion? Then they'll take this particular force and just look at the y part and the x part. You don't have to worry about that, but you do need to recognize gravity. You do need to recognize normal force. We will need to understand that friction can be applied. Okay? If friction is applied, that's going to definitely decrease movement. It decreases velocity. It acts against the force that's moving something. Okay, and then we have applied forces where, you know, maybe we're pulling a trailer. Okay, maybe you're pushing a wheelbarrow. Okay, so right now, let's look at Christian's water bottle here on the table. Okay, what forces are acting on that water bottle right now?
Normal force and gravity.
Normal force. What direction is the normal force acting?
Up.
Normal force is up. Is that a push or a pull?
Push.
So the normal force is pushing up. Gravity is
Pushing down.
pushing down. Are there any other forces? Not right now. Is it balanced or unbalanced forces?
Balanced,
How do I know they're balanced?
because
gravity
one pushing up while the other pushing down
Okay.
at the same, like at the same.
At the same? How do I know that?
Because down means negative and up means
Okay, but the thing is, what happens if these were different values? What if, for some reason, one of the pushes, what was that?
It would be an unbalanced force, cause like if it,
No, actually, I agree it's balanced. I just wanna know how we can know that it's balanced.
if we're standing, if I dropped it.
Well, if you dropped it, it would start moving in a particular direction. If I tried to drop it, I wouldn't have the normal force underneath anymore. And it just had gravity acting on it. And if all I had was gravity and maybe some air resistance, you know, if you drop something, you can have air resistance, which is a friction too. Okay? But it's still gonna keep moving. If it's moving, it's unbalanced. If it stays still,
it's balanced.
it's balanced. Forces cause movement. An important point, right? If I have a moving object, forces will be unbalanced. It means that there is a force that is acting on an object, okay, some unbalanced force that allows it to move. Okay, so like if I have a person that's pulling me and a person that's pushing me and I'm trying to stop and I'm trying to apply some friction but I'm still moving, we have an unbalanced force. If I have two friends that are pulling this way and pulling this way, but they're pulling with the same amount, although I feel like I'm being pulled apart
You're not.
and I'm not moving, the forces are balanced. So right now that water bottle sitting on a table has balanced forces. How do I know? It's not moving. Okay, if I take this meter stick that's on the ledge here, and right now, forces are balanced. Gravity's acting down, normal force by the surface of this ledge is acting up, balanced. But I apply a force from the left here. Do I have balanced forces anymore? No, I've added a force that's moving it to the right. Unbalanced force means something's going to move. Balanced force, and I have to look in the X direction and the Y direction. I need to make sure that all of my pushes and pulls, make sure that my net force is 0 in both directions. If not, something's going to move. If all my forces in my X direction are 0, all my forces together in the Y direction are 0, then it's just going to stay there. Do I have a reasonable idea about how to do step 1 of the test? I hope so. You can pick any object. Any object. Tell me. Okay. What forces are acting on it? Do we have gravity? Do we have normal force? Is there the force of the car's velocity moving down the road? Is there friction with the road? Is there friction with the floor? Okay, is there motion because of the force applied by someone's hand?
You know how when there's like when something shakes an object, what is that? Is it like there's the force passing through all the solids, and that's why it's shaking?
I think that's a little bit more complicated question. Could you be more specific as to what type of thing is shaking?
Let's say can.
Okay, so you're saying like a can's on the table and there's some sort of motion and it shakes?
Yes.
What that has to do, like say, like we have an earthquake?
Yeah.
And we have this shaking going on. The reason for that type of motion has to do with the fact that energy, even though the motion wasn't directly applied to it by what's caused the earthquake, and energy is, transferred using waves, okay? Just like, you would expect to see a water wave, and we're gonna talk more about waves a little bit, I guess, in the future, especially as we look at electromagnetic radiation. But you have waves where we have things that if we were to graph it and say that this is the X and this is the Y, we have things that go in both directions, positive, negative, that this energy gets transferred, that it's already oscillating, kind of like a fan, okay? And so that's going to cause that shaking even of an object because the movement as it hits is going to be not constant. It's not just going to be like one push. Does that make sense?
Yes.
So it's a little bit more complex, and we're not going to get into all of that just yet. You study more physics, A lot of foundational physics is really easy, I think, for all of you guys to understand. You just gotta be patient with it. And it's just not something that we have time to go into as far as this goes, but we will learn more about waves. Everything that you are thinking about right now really is motion due to waves. And we can have physical waves, like I said, what you could see for water, or if we get a string or a rope and we shake it up and down, we can have physical waves like that. But there's also sound waves, how sound travels is still using waves, but it's a different type of wave than those physical waves. And then all light and energy that we see, and even beyond, like X-rays and microwaves, all of that is waves, where we're transferring energy. So that's a whole lot of study in a whole lot of areas. And we can talk more about that another time, okay? So we talked about the water bottle. How about if I have a ball that is just falling to the ground? If I have a ball and I let go of it and it's falling to the ground.
Yeah, I'll talk to you soon.
So we have gravity, the force of gravity, pushing it down. And then she added, hey, I also think that there's going to be something pushing back up, which is the force of air resistance. And if I have a ball and I let go and it's falling, is that balanced or unbalanced? Unbalanced. How do I know? Because it's moving. That would be really weird if air resistance were that strong, it could overcome gravity. You'd have to have some really thick air, right?
Could that happen?
Not that I'm aware of. I can't think of. You'd have to get the right mix of gases to get the density thick enough. I don't think you could. What happens though if we change this and we have the surface of the water and we have a ball that's floating on it? What are the forces? We have a ball that's floating on the water. Do I have a force acting in the upward direction? Yeah. So we have the force acting from the water of the surface of the water, and we still have the force of gravity. Now, if this was not moving, would you say the forces are balanced or unbalanced? Hey ladies, I don't know why you're deciding to nap. Harmony, Denia, please sit up. Is this stuff you all know? Denia, could you please sit up? I will wait for you ladies. Please sit up. If we need to put our blankets elsewhere, we're here in class. Okay, if this were not moving right now, are the forces balanced or unbalanced?
Unbalanced.
If the
I
force,
mean, balanced.
how do you know that?
Because it's not moving.
Because it's not moving. Okay, what happens if I have some wind blow on this? What will happen to that ball?
It would start moving.
Okay, this would start moving to the right, really, but I understand where you're going. It would start pushing it this direction. Why?
Because the air is moving.
Yeah, it's moving. We have unbalanced forces because There's nothing acting in opposition to it. There's nothing that's pushing back. Okay? How about if I have a ball that's rolling? So I have the ground, and I have a ball that's rolling across the floor. Harmony. What forces? Hey ladies, if you need to stand up to stay awake, I don't know what's going on today. Normally when we have discussion, you're right into it. I'm not including you, I'm saying ladies. Okay? Are you able to answer my question? Why not? What's with today? If you need to stand up with your notebook, take some notes over here or something, let me know. I'm not trying to get you guys in trouble, I just wanna make sure that you don't miss something. So Denai, what forces are acting on that ball right now? Can you name one for me?
Normal or gravity?
Which one?
Normal.
Which direction is normal force acting?
Like, I mean, is the ball rolling?
The ball is rolling.
So, that way?
You're saying there's a normal force going that way?
Wait, no, going back. I don't know.
Okay, you want to try gravity?
Sure.
So that's another one that you told me about. What direction is gravity acting on the ball?
Down?
You're saying that with confidence?
Yeah.
Are you sure?
Yeah.
Gravity always acts down. Yes, straight down. Back down. There's no other way. Gravity can't act sideways. Doesn't act up. It's always going to be down. So you can be confident.
Net force to the right.
Yes, there would have to be a net force. Now, net force isn't a force unto itself. You are right about that there is net force. Net force. That is in the positive x direction. Like there has to be a overall net force that is moving the ball this way. But that's because of a combination of these other forces that are acting on it. Does that make sense? So we have the force of gravity. What's this thing here? Like in order for that to roll, I need to have a force that is the force of the rotation because the ball is rolling. I can also call it a rolling force. I'd be okay with that. Okay? Rotation or rolling. I think we're still missing some forces.
Wouldn't there be friction?
Yes. There has to be friction. Now, if the ball is going this way, that means the friction is going to be coming the other way. So I'm going to have a force of friction with the floor. Force of friction. The floor is going to have some friction against that ball that takes away from the velocity. Otherwise, the ball would just keep rolling forever. The friction slows it down.
Wow, wouldn't there be slime friction?
In this case, it would be rolling friction. Okay, we haven't looked at that too deeply yet because that's the next set of notes that you have due. Where we look at the different types of friction. There's sliding, and there's rolling, and there's static friction. They tell you about sliding, static, fluid, and rolling. Okay? So if we were to look at different types of friction, okay, sliding, static, fluid, and rolling. So rolling is anytime I have something with wheels, or something that is a
Something
sphere.
that's just-
Okay, this is going to involve wheels or spheres when they're moving. Anything that has wheels or spheres and it's moving, there's rolling friction, because it only has friction with that one little part that's touching. Okay? So rolling is only where the sphere, the ball, or the wheels touch another surface. Fluid is go like this, really fast. Do you feel like you're pushing against something?
Yeah.
You can feel the air, right? That's fluid friction. If you're doing that in water, would you have a harder time?
Yes.
Yeah, because liquid is more dense, you'd have even more friction. That's why people do water aerobics, okay? Because there's a lot of friction, but there's a lot of support because of the density of the water, okay? So this is in contact with everything. Static. Okay, static friction, you only notice when you try to start pushing something especially heavy. Like, have you ever tried to move a piece of furniture where you gotta slide it across the floor? And you're like, ugh, and suddenly it starts to move? Okay? That, trying to overcome to get it moving, that static friction is that friction to get it started. When things are just sitting there, like this is sitting on my hand, okay, there's a larger amount of friction to get it moving than it takes to keep it going. And so the larger the objects, the more static friction we're gonna have. The heavier the objects, more static friction we have. Proportional. And then sliding, we have the entire surface touching the entire surface. Okay, so this ball has rolling friction. If these wheels didn't turn though, and I wasn't coming into contact with, this is a ball. If the ball wasn't turning like this, like when it's rolling, if it just slid across, you know how sometimes something could just slide and not even change in position? Just slide, that would be sliding friction. Like sliding into home base. Okay, would be sliding friction. We're still missing a bit. We're missing, I think, at least two more.
Wait, you said it was a force, right?
I said what?
Didn't you say like it's a force?
What's a force?
Well,
Yeah, we have the rolling of the ball because of a force that was applied. We have gravity acting down. We have friction with the floor. We also have, acting in opposition, the friction of the air. Our air resistance. Right? Air resistance is still going to slow it down a little bit. And then the one that people were unsure of, keeping the ball up, always perpendicular to the surface. We have surface meeting surface, the normal force. Now if this ball's rolling, do we have balanced or unbalanced forces?
yeah, unbalanced.
Unbalanced, because it's moving. So, balanced forces, not moving. Unbalanced forces is moving. I could have just one force, well, actually I'd have a hard time getting just one force acting on something. I could have like very few, like 1 or 2. I could have 10 different forces. We could all come and stand around one of the tables and all like put our hands on the table and push down. And each of our hands would be applying a force to the table. And we'd have to consider each of those forces as we consider the net force. Okay, I'm pretty sure though, even if we did that, could we figure out the net force of this without knowing the individual forces? If we all push down on the table, the table is pushing back up so that it doesn't move. That normal force is going to be the same amount as our forces pushing down. It's not moving, it's still going to be balanced forces. So let's look at something known as a free body diagram. And it sounds kind of like a weird name, but what we're going to be doing is we are going to take an object and just consider what forces are on it and not consider anything else in the picture. Okay, a free body diagram is where I take an object and I just consider any pushes or pulls that may be acting on it. So this one looks kind of crazy, doesn't it? This has all these different forces acting on it. And if I gave these values and said this was 5, this one was 2, this one was 2, this one was 3, and 9, and 27. Could I figure out the force that is being applied and what direction this particular object might move? I can. It's gonna take us a little bit, huh? What scares you about that? Just because there's so many numbers and so many different directions? I don't blame you. So rather than tackling this, how about we look at this first?
Okay.
What direction is that box going to move? Now this is known as a free body diagram, because we're just kind of like suspending this thing in space and looking at what are the forces that are acting on it so that we can calculate net force. So this one here, what way is that object going to move? Harmony. You know, Texas? It's gonna move down. Because the only force acting on it is pushing it down. There's nothing else to hold it up or move it left or right. Okay? How about now? Which way is this one gonna move? What do you think, Jack?
Stand still,
Why?
because the forces are balanced.
The forces are balanced. Anytime where we see these different forces, we add them together.
And then
10, 10, negative 10, positive 10. Oh, same thing. Right?
So what's the 0?
So this is net force of 0. You're right. Okay? Net force equals 0. And this means that the forces are balanced. Okay, what if we go 10 newtons? 10 newtons. What happens to the object, Kenneth? This one right here, if you're paying attention. What way is that going to move? To the right? You think think it's not gonna move?
No, because it's all going the same amount.
So he's seeing equal numbers, so he thinks it's not gonna move because of those equal numbers. Bella's itching. I think I'll give her a chance for a change, and I know Christian's right behind her.
It's to the right and down.
So, what Bella says, and Christian was ready to say it too, they both say that, hey, the net force is this. Because I have this moving 10 to the right and 10 down. So it's going to be moving down and to the right. I have a net force in the x direction of 10 and a net force in the y direction of negative 10. Let's put it down. Okay? How about if I have this? What direction is it gonna move?
It won't move.
He says it won't move. Who
gonna
else
go-
agrees with that?
I think it's gonna,
Denia, what do you think's happening?
I think it's gonna go down.
You think it's gonna go down?
Yeah.
Does it move left or right?
No.
Just
because
down?
they're- Yeah.
Yeah, again, x direction, these are balanced. This one doesn't have a force acting up against it. Okay? How about this?
Yeah,
It's
now
not
it-
Hold on, you don't even know what the amount is yet.
Oh, it
gonna
would
go
be
up.
going.
It's gonna go up. You're right, 2 newtons up. So, what's happening with this one? Since everyone is backing out, even though the bell hasn't rung,
It's going down.
you're saying it's going down?
No.
It's down to the right.
It's going down.
Okay,
Well,
Bella says it's doing this.
Yeah.
She says down and to the right.
Yeah, it's
Going
going down.
It's going down.
Down.
You think it's more down? So you're thinking more like,
Right?
Yeah.
okay, more down than it is because 27 compared to 12. So this is negative 15 in the y
Wait,
direction.
but don't you do like 9 plus 27 because they're both going down?
Oh, you're right, you're right. 27 plus 9, that's 36, subtract 3.
33.
So this is negative 33 down. And we have only 1 to the right. So yeah, this is actually big time, down, down, down. A little to the right. Dude, you were killing it today.
Killing it.
Did you do a bunch of reading or what? Seriously. You were on fire. I need to send an envelope to Mom and Miss Banks because you were on fire today. So were you, as ever. As ever. Oh, and time to turn off. That's my science. Bye. We'll see you later.